Okay, so I got this idea of Hooke's law of springs, and I got this graph that pops up right away. By the way, this would be a graph of what? Ideal or non-ideal spring? Non-ideal. Not ideal, and I can tell that it's not ideal because it's not linear. Sometimes when you look at a spring like this, we want to be able to explain in our own words what's being shown in the graph of a spring. Is it ideal? So you guys telling me it's not ideal. Does it become more stretchy or more stiff? And I want to propose that for this spring, there actually are portions, or at least a portion, of the graph that behaves ideal. So long as we don't stretch it too much, it behaves ideal. And we could say that there's limits to the ideal nature of this spring. If I'm just counting squares, let's just pretend these squares are 1, 2, 3, 4, 5, 6. Let's just say that these are meters. That would be a ridiculously large spring. But if they were meters, the spring can distort by 9 meters. That's a wicked spring. But at how many meters would you have to stretch this thing from its unstretched length before it stops behaving ideal? Where does the ideal range end for this? Yeah? 3? You guys see he says it's at the 3 meter mark? Stops being linear? And something that you could do is you could take a ruler and you could just lay it down and see when it diverges from the straight line. Do you see that by 3 it's diverged a little bit already? So if I was going to pick on this thing, I could say, okay, well, maybe 2. Maybe 2 is where it diverges from the straight line. That's when it stops being ideal. And people say, okay, well, why would it stop being ideal? Well, if this was a bungee cord, let's just say, after a certain point, it stops behaving ideal after it's been stretched by 2 meters. This thing says that after it stops being ideal, something else happens. Maybe I could put a little bracket here and say, for here, ideal. From there to there, ideal. But after that, something else happens. Think about a graph that we've looked at previously. In the next portion, is it becoming more stretchy or less stretchy? What's that? More stretchy? Let's see. So look, this slope is very steep. This slope is less steep. If it's less steep, doesn't that mean that it has to use less force to stretch it? Turns out that in this range here, if it's getting less and less steep, I could say that it's getting less stretchy. Oh no, getting easier to stretch. Would that be an easier way to say it? Maybe I'm confusing myself with my language. Getting easier to stretch. So more stretchy, you're saying. I get it, yeah. Getting easier to stretch, more stretchy. The number of newtons it takes to stretch it is lower and lower. And if you wanted to take a look at this quantitatively, if we had real data, we could go and we could make a series of tangents even. We could say, okay, well, at this point, it's this stretchy. At this point, it's instantaneously, oh, wait a minute, I got my ruler up there. Oh, look at that. Can you see that during that range, my ruler lies flat against I call it a curve. Can you see it's flat against it, though? It looks like, where is it flat for? Looks like it goes up to about here. Can you see that? It looks like it becomes ideal again. This is an interesting spring. Maybe this is a bungee cord. Maybe it's a spring. But it seems like it's ideal sometimes and not ideal other times. You see that in this range it would have one K value. We'll call it K2. In this range it would have a K1 value. And then in between it wouldn't be ideal. This is an interesting spring to investigate. I'd like to get my hands on this spring, And I'm not quite sure why it behaves the way it is. And we could talk with some material scientists and maybe some people that are really into polymers, if it's a rubber band or something like that. Maybe people that are into metallurgical sciences, material sciences, to talk about why this would happen if it was a metal spring. But this is an interesting spring. So it becomes ideal again. Weird. Anyway, so let's make a little note about this. The spring appears to behave ideally. For 2 different force ranges. We could say, but overall, it becomes less stiff. Less stiff. We could say easier to stretch. As we apply more and more force. So that's a non-ideal spring, and we've got to be thinkers to be able to investigate that kind of thing, because we're going to encounter not ideal things in this world, right? I got another graph. Again, I don't want to apply numbers to it. I just want to use it as a tool for conversation. So I say, if I did have an ideal spring, so back to this ideal spring idea, we would have the whole way along uniform slope. And that's basically the best way to investigate if it is an ideal spring, because the slope doesn't change as we progress with more and more force and more distortion. And I said this out loud, but K is a characteristic of that specific spring. When we're talking about for an ideal spring, the spring slope is constant for the spring. But for a real spring, we might say that it's constant within its ideal range. I'll put that in quotes, because there's going to be a range of values for which you go beyond its ideal range. And I have some metal springs in the cupboard over here in the classroom where people thought they were showing how strong they were, and they pulled on those metal strings so hard that they got ruined. They went beyond the ideal range. They actually caused long-term damage to the springs. They wouldn't go back anymore, but they definitely went beyond the ideal range. Slope is always going to be Fs over delta of delta x. It's always going to have units of newtons over meters. How many newtons does it take to stretch it by how many meters? The number of newtons required to distort a string by 1 meter. And so for most springs, we're going to have values that are going to be within a human, or most of the springs we deal with are going to be within a human range of ability levels to stretch them. But of course, there are some really strong springs. And if you wanted to give this a name that isn't very sciencey, we could call this the stretchiness rate. Anyway, but that was slope, and it's called the elastic coefficient. Okay, and as I said before, spring constant and spring coefficient, common synonyms. All right, I want to talk about a new thing, the area, because here we are like obsessed with slope, but I want to talk about area. If I have an area of Fs versus delta x, we're talking about this shaded in portion right here. Let's just say that we had numbers on this graph. I'm not going to put numbers on it because we're going to talk about it really more in theory, but it's going to show up in homework. I know that I've got this equation, Fs equals K times delta x. I want to actually think specifically about delta x max. So like this point on the graph. And I would like to say that Fs, let's just throw in that subscript, max, is going to be equal to K times delta x. You notice that I didn't put the negative sign in there? Because I just want to talk about how big the value is. There's no negative forces going on in this graph. I know from other times in my life that the area of a triangle is base times height divided by 2. Some people write that as 1/2 base times height. That's fine. This particular triangle would therefore have a area of 1/2 times delta x max, because we're talking about the maximum stretch length. Maybe I should throw that word max in down here as well. So delta x max, the base, times fs max. And I'd like to sub in equation 1 into that expression, because that's just an expression that talks about the area of this triangle. What could be so wrong with that? I say, okay, well, the area is going to be calculated, therefore, as 1/2 delta x max times, in place of fs, k times absolute value of delta x max, close bracket, and we end up getting 1/2. You know what, I'm going to collect the delta x maxes together, put the k out front, delta x max squared. And if you look at this area, I'm going to continue to just call it area for a second. But if you look at the units for this area, let's just do that for a second. We've got 1/2 k delta x squared. If I look at the units, k we all know has units of newtons per meter. Delta x, because delta x is in units of meters, is going to be delta x squared would be meters squared. I do a little bit of calculation here, get some canceling out of the way, cancel, cancel, and I end up getting units of Newton meters. Now, once upon a time, we looked under the hood of a Newton to say that it was kilogram meters per second squared. We multiply that by meters, and you end up getting kilogram meters squared per second squared. And if we're looking at all of this in unit analysis, does anybody know what kilogram meters squared per second squared is equal to? I heard it. Say it out loud.
Joules.
It is joules, yeah. These guys are joules. Capital letter J, because it's somebody's last name, but these guys are joules. So when I go to look at this formula that was just an area calculation, really, we've calculated the elastic potential energy stored in an ideal spring, and we can call this ES equals 1/2 k delta x squared. Now, if you're somebody who's really into calculus, you look at this, and maybe there's nobody here that's into calculus, but if you were into calculus, you might say, oh, I recognize something here. If I take the first derivative of elastic potential energy with respect to delta x, you end up getting first derivative of 1/2 k delta x squared over delta x, and that ends up being k delta x. And the only reason I mention that is just to say, hey, look, it takes us back to k delta x, which just means that the force formula for springs is the first derivative of the energy formula. That's all. And if you're not into that at calculus yet, then it doesn't matter, but one day you will, and one day that'll make sense, all right? And that's good.